Hi, Maxine Joy.
Hi, Dr. Good. How are you?
I'm good. How are you?
I'm good, thank you.
Have you been working all day?
Actually not. There was a CIS department tour for the Milipoma Sigma site, so that's
Oh,
where I was. I'm working a little later today at 11 till tomorrow.
oh my gosh. Holy cow. All right. Well, listen, we are here, so let's use this time to help. Uh, Isaiah, I see you're here too. I'm glad to see that you're here.
Yeah, thanks, Professor Good. How are you doing?
I'm good. I'm glad to be here with y'all. I'm going to let Maxine Joy start it off with the first question, and then we'll just go from there. Is that okay?
Yeah, that's good.
Is this in focus okay?
Yes.
Yeah.
Great. All right, Maxine Joy, do you have a specific question or topic or something that you need to talk about?
Yeah. My little problem was, well, while I was working through the um special homework, the one we just did this week, wanted to ask if you could go over the standard SFF, the
Standard
factorization.
factored form?
Yeah.
Sure. All right, so let's just talk about standard factored form. We learned a lot, and I can understand if you missed that lecture, how those lecture notes might have seemed quite heavy because there was a lot of notation, right?
Mhm.
And
Yeah.
this is the idea. Um, let n be an integer. Now, we know that if an integer is bigger than or equal to 2, then we can assign it a label. Either it's prime or it's not, if it's at least as large as 2. So we're going to talk about these integers that are at least as big as 2. If you've got such an integer, it might be prime, right? Like 2, 3, 5, 7. Or it
Hmm.
might be composite, like 6, 15, 22, right?
Hmm.
So what what the unique factorization theorem tells us is, hey, if we're looking at one of these integers that's big enough, there exists a unique way. It means there's only one way to do this,
Hmm.
to write in as a product of powers of primes in order by size. So n, okay, so we can kind of do a running example at the same time. Okay. So while I write the theory, we're going to do a little example. All right. And I need my calculator. Hang on. Because I'm going to cook up an example on the fly here, and I need a calculator. Okay. So let me just do this. All right, we can do a big one. 163,800. So, 1,638,000. Certainly big enough. And what it says is we can find all the primes in N and we can put them in order by size. So P1 would be the smallest prime factor. Can you see what the smallest prime factor of this is? Just because of the fact that this is an even number?
Me too.
Yeah, two. So P1 would be two in this case. But there might be a bunch of twos that we can factor out of that. So however many twos we can factor out of n, that's the exponent on the two. We just call that E1 because the ones match. So it's the first prime factor raised to the number of copies that fit into n
Okay.
times the second prime factor, P sub 2, raised to the E sub 2. And you just keep on doing that until you get to the very biggest prime factor of the number n, whatever it happens to be. We'll just call it P sub k.
Mhm.
And then it's raised to its power because maybe there's several copies of that that fit into n. Okay?
Mhm.
And then the point is these P sub 1, P sub 2, up to P sub k, these are primes. So the P sub I are all prime. I'm just, instead of saying P1, P2, dot, 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 PK, I'm just saying P sub I, and that's for I ranging from the 1, that's the first I, all the way up to the K. Okay, so that's the way we say that. So we learned some notation. The, the other thing we want to do is we want to say, hey, we're going to put these primes in order by size. The first one's going to be the smallest prime. The second one's going to be the next smallest, all the way up, and the P sub k is going to be the biggest prime. And the way we say that is we say P sub I is less than P sub j whenever the I index is less than the j index. In other words, one, that indexing number one is less than the indexing number two. You agree?
Mhm.
So the one is like our I, two is our J. Well, that this says that P sub one is going to be less than P sub J because P sub one is going to be less than P sub two because one is less than two.
Mhm.
See what I mean? And
Yeah.
and one is less than K. So P sub 1 will be smaller than P sub k. Well, 2 is less than k, so P sub 2 will be less than P sub k, and it goes all the way up. See how that works?
Yeah.
And this is just the range of the indexing variables involved in that. And then the last thing we want to say is, hey, these exponents, they have to be at least as big as 1. We don't want to have like a 0 exponent. So we just say the E sub I is an element of Z plus. That makes sure that we don't use any weird exponents that are smaller than 1. Okay?
Mhm.
That's all that all says. And it looks like a lot, and it kind of is. But it's interesting. It gives us some interesting results about perfect squares and perfect cubes shortly. All right, let's take a look at this number. Since we know we want to pull these primes out and eventually list them in order, let's just start with the very smallest prime and ask ourselves, hey, uh, what is the smallest prime again?
Two.
Yep. Let's ask ourselves, does 2 factor out of this? And sure enough, it does. N is 2 times, and now I'm using my calculator, and that's fine. I'm just gonna uh, I'm just gonna take that answer and divide it by 2. All
Mhm.
right, so 819000. Okay, so we're on our way.
Mhm.
Well, 2, of course, we can't break that down any further. It's a prime. So
Mhm.
we look at this factor. Let's just stick with 2 until we can't pull any more 2's out. Can we factor 2 out of this?
Yeah.
Yes.
Sure, it's even, right? So let's divide that by 2. And so this is going to be 2 times 2 times what, 409, 500?
Yeah.
And then we ask the same thing. Can we pull another 2 out?
Yeah.
Yeah.
Yeah. And now we're left with 2,
204.
8. Oh, is it 204? I
Yeah.
can't even read it. Old Dr. Good getting old over here. Okay. 204, but you'll keep me honest. 750. All
Mhm.
right. Can we pull a 2 out of that?
Yeah.
Yeah.
Mm-hmm. Isaac was like, yeah. That's great. Now we got 102375. Can we pull a 2 out of that?
No.
Mhm.
So now we're going to move on. What's the next prime after 2?
3.
Three.
3. And we learned an interesting little trick, Maxine Joy. This might be hard to see whether it's divisible by 3. Now, of course, we could just use our calculator, but here's a really handy little trick. If
Mm-hmm.
we add up all the digits of this number, if the sum of those digits is divisible by 3, then this number is divisible by 3. So let's do it. 1 plus 2 plus 3 is
6.
6, plus 7 is 13, plus
Mm-hmm.
5 is
18.
18. So does 3 divide 18, folks?
Yeah.
Yeah.
So we know 3 is going to divide this. So I don't even mess up my calculator thing going on. So now we're going to divide this by 3 and see how many times 3 fits in there. It's 3, 4, 1, 2, 5. So yeah, so let's
Yeah.
add these up. Just 3 divide what? 7, 8 plus 7 is 15. Yeah,
Yeah.
right? This is add these digits together, we get 15. That's divisible by 3. And if you don't want to keep writing 2 times 2 times 2 times 2, we can write 2 to the fourth, right?
Yeah.
Yeah.
All right, so we'll pull another 3 out, divide by 3, and now we've got 11375. All right, so does 3 divide 1 plus 1 plus 3 plus 7 plus 5?
2, 5, 12,
17. Yeah, no, it doesn't, does it?
3,
Mm-hmm.
4.
Because that wasn't that 17 if we add these up?
Yeah.
5
Yeah.
plus 5 plus 7. All right, so no more threes. So we can write 3 squared now. We're done with the threes. All right. So what's the next prime?
5.
5.
Is this divisible by 5?
Yeah.
Yeah, because it ends with either a 0 or a 5. So we know
Mm-hmm.
we can factor a 5 out of that. So let's divide this baby by 5. And now we've got 2275. So stick with the 5s until we've exhausted them. Can 5 divide into 2275?
Yeah.
Of
Yeah.
course. 2 to the fourth times 3 squared times 5 times 5 times
455.
455. Can 5 divide into that?
Yeah.
Yeah,
Yeah.
it ends in a 5. So let's divide by 5. And we're going to get 91. So now it's 2 to the fourth times 3 squared times 5 times 5 times 5 times 91. So we've got 2 to the fourth times 3 squared. We're done with our 5s. There's 3 of those, so it's 5 cubed. And now we got to look to see what divides into 91. What's the next prime?
7.
7. 7 doesn't divide into 91, right? Because 12 times 7 is 94.
Yeah.
11 times 7 is, no, 12
Mm-hmm.
times 7 is 84.
Yeah.
13 times 7,
It's
ooh,
91.
is
Yeah.
91. So this is 7 times 13. Let me check it. Yep. And these are all primes. And we're done. So let's just try to compare this to this, okay? So
Mm-hmm.
what's P1? What's our first prime?
2.
Yep, P1 is 2. What's our P2?
3.
What's our P3?
5.
What's our P4?
7.
And what's our P5?
13.
So K, which is the total number of prime factors, is what?
5.
Yep, we got 5 prime factors. And P1 is 2. What's E1?
4.
Yep, see, you're getting it. You understand it, don't you? P2 is 3. What's E2?
2.
Nice. P3 is 5. What's E3?
3.
P4 is 7.
7.
What's E4?
1.
Nice. And P5 is 13. And E5 is.
1 as well.
So does that make more sense now?
Yes, please.
That makes sense. I have one question.
Please.
Because 91 goes into 13 times 7, you ordered it as still 7 before the 13 when it comes to RPs.
That's correct.
All right, I just want to make sure I highlight that.
Because we want to make sure P4 is
Before it's
less than
that
P5
P1.
because
Okay.
4 is less than 5.
Yeah.
All right, so I just want to make sure that I highlight that so that I don't mess that up. Yeah.
You got it. And so then if you do look at the notes, we had a nice little fact. It turns out if we have a perfect square, then every exponent in its standard factored form has to be divisible by 2.
Hmm.
And did you see the notes on that?
Yeah.
Yeah.
Shall we go through that?
Yeah, we could do that.
Okay. So here's a fact. If x greater than or equal to 4 is a perfect square, then every exponent in the standard factored form, by the way, this is called the standard factored form.
Hmm.
Okay. Every exponent in the standard factored form of x is divisible by 2. So why is that true? Okay. Mhm. All right. Well, let's answer that question for ourselves. All right. Since x is greater than or equal to 4 and x equals n squared because x is a perfect square, that means it's equal to n squared for some integer n.
Hmm.
We know that this n has to be greater than or equal to 2 because x is at least 4. So that
Hmm.
means, hey, n is big enough to play the unique factorization game with. So n has a standard factored form. And if we write n with its standard factored form, it's P1 to the E1 times P2 to the E2 times up to some, P sub K to the E sub K. I won't write all the stuff about, hey, the P's are primes, the exponents are greater than 0. Okay, but we know that. Then let's look at x. X is n squared, right?
Hmm.
Well, n is this whole big thing. Now it's getting squared. That's what x is, right?
Yeah.
So we use the laws of exponents because we've got all these exponents going on. And we can take the 2 and distribute it across the factors. Let me just write the rule. Laws of exponents. There are a couple of laws of exponents that we use. One of them is that if you have like A times B, whole thing raised to the K,
Hmm.
then you can take that K and apply it to all the factors. So this is the same thing as A to the K times B to the K. Do you remember that rule?
Yeah.
And there's another rule that says, hey, if you have something like A being raised to an exponent K, and that whole expression is getting exponentiated again, raised to another exponent, well, there's a rule for what we do with these exponents. Do you know what that rule says?
Multiply them.
Multiply that
Exactly.
exponent.
Multiply them. Okay. So these are the two rules that we're going to use right now. We're going to start by using this rule that says if you have an exponent where you have a whole big product being raised to that exponent, then that exponent can get applied to each factor. It can be more than 2. This is just the rules just for 2, but you can do it for a whole bunch. So that means these factors are these that are getting multiplied together, okay?
Mm-hmm.
So that means P sub 1 to the E sub 1 is being squared
Okay.
times P sub 2 to the E sub 2. That's getting squared. All the way up to the last factor, P sub K to the E sub K. That's getting squared. Does that make sense?
Yeah.
Mm-hmm.
Now we get to use the second rule that says if you have an exponent being raised to an exponent, you can just multiply those together. Now, when we multiply a variable like E, so whatever, and a number, when we do multiply them, we generally write the number part first,
Okay.
right?
Mm-hmm.
So check out what's happening now. These are all, this is all an expression for X, but it's based on the fact that X is a perfect square and N was big enough to play the standard factored form game with. Check it out. See these exponents now? This
Mm-hmm.
is the standard factored form of X. These primes are still in order by size. We've still gathered all the copies of each prime together with an exponent that's greater than or equal to 1. In fact, these exponents are all greater than or equal to 2. See that?
Mm-hmm.
So
Yeah.
this is the standard factored form of X. And what do you see is going on with these exponents? Notice 2 divides 2e sub I for each e sub I. Do you see that?
Mm-hmm.
Yeah, I mean, 2's right there is one of the factors.
Yeah.
So every exponent in the standard factored form of a perfect square is divisible by 2. And it turns out you can play this game with perfect cubes too. Like if x is a perfect cube, it would equal n cubed, right, into the 3.
Yeah.
Mhm.
Yeah.
And instead of having a 2 here, we would have a 3 here.
Mm-hmm.
And that 3 would get distributed. And then it would be 3e sub 1 and 3e sub 2. So when x is a perfect cube, what could you say about every exponent in its standard factored form?
It would be divided by 3.
That's right. That's 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 the next fact. And although I didn't prove it, you could now try to prove it, but at least you have that under your belt because I think there's a WebAssign problem where it asks about perfect cubes and it talks about it goes through this whole thing again. So if x greater than or equal to 8, it's got to be at least 8. So its cube root is big enough. So its cube root is 2 or bigger, is a perfect cube instead of perfect square, but a perfect cube. Then every exponent in its standard factored form is divisible by 3. I've said it a little bit differently, but it's perfectly right. Okay. All right. Isaiah, it's your turn to ask a question, unless anybody has any questions on this.
Give me a second. I'm gonna look at our special.
Okay, so while you're looking, Maxine Joy, there was another question on the homework about finding the smallest positive integer k. It would,
Yes.
and that's all tied in with this, so we might as well look at one of those.
Okay.
So here's the smallest positive integer k game. All right, so it's that first example that we did here. We'll call this one example 1. Okay. Here, I'm going to say let n equal that. Find the standard factored form of n. I guess it would have been helpful for me to at least write what we were doing over there. Okay. For somebody that's just going to look at the notes, you know?
Yeah.
All right. Okay. So here we go. Find the smallest positive integer k that will make x a perfect square when this is what x starts out as. X is going to be 2 to the 7th times 3 times 5 squared times 7 cubed times 11 to the 4th times 13 to the 5th times k. Okay. Bigger than we need, but hey, we'll get plenty of practice. Okay, so this is the idea. The idea is to build k so each exponent in the standard factored form of x is divisible by 2 because we know that that's what's going to be true if x is really a perfect square. Each of
Mhm.
these exponents actually needs to be divisible by 2. So in some sense, k is our correction factor. All right?
Okay.
All right. So prime factor we see, and then what we need to add as a factor of k. So we'll make a little chart. All right, so let's start with the first prime factor that we see. The first prime factor we see is 2 raised to the 7th. All right, 2 to the 7th. 7 is not divisible by 2,
Mm.
but we need to have an even number of copies of 2 here if this is going to turn out to be a perfect square. So as we start to build k, we're going to add a copy of 2 into k so that it'll be 2 to the 7th over here, but then
Mm.
k will have a 2 to the 1, and together 7 plus 1 will equal 8,
Yeah. Okay.
right? Because we have this other law of exponents that says that if you have a to the m times a to the k, then we just add those exponents together, right? So
Yeah.
when we have 2 to the 7th times 2 to the 1, we'll have a 2 to the 8th, and 2
Mhm.
divides 8.
Yes.
All right, so let's take a look at 3. Right now we see a 3 to the 1, right? So
Hmm.
do we need to add any copies of 3 into the k that we're building?
Mm. No.
Wait a second. Is 1 the exponent on the 3? Yes.
Yes.
Does 2 divide 1?
Oh, no.
Right? We gotta bump them up to make them even if they're not
Hmm.
even. So what do we need to add in as a factor of k?
3 to the 1.
Yeah, because I mean we could even add 3 cubed and then we'd have 4 copies of 3, but we don't
Yeah.
need that many and we're supposed to find the
Mhm.
smallest.
Okay.
All right. So now let's look at so we've corrected the 2's, we've corrected the 3's. Let's look at 5. We've got 5 squared. How many copies of 5 should we add as factors of k?
1. Or no. We could add 2.
We could add 2 because then we'd have 5 to the 4th. It's true. We
Hmm.
could add 2. But do we actually need to add any factors of 5?
No, because two divides itself.
So none needed. Okay.
Okay.
7 cubed. What should we add to k? Anything?
Okay, add 7 to 1.
Perfect. 11 to the fourth. Do we need to
No.
add any 11s?
No.
Good. 13 to the fifth.
Yeah, we could add 1.
Great. So our answer is that k is going to be 2 times 3
Mhm.
times 7 times 13. And now we're going to check. We're going to check and make sure this really worked. So x is 2 to the seventh times 3 times 5 squared times 7 cubed times 11 to the fourth times 13 to the fifth times, k, which is 2 times 3 times 7 times 13. So if we gather these together, it's 2 to the eighth times 3 squared times 5 squared times what's the power on the 7?
4,
Good. What's the power on the 11?
4,
And what's the power or the exponent for the 13?
6.
And now we can check and show that this is really something squared, right? Because we're trying to show that it's n squared,
Mm-hmm.
right? So when we pull a 2 out from each of these exponents, tell me what's left behind. It's 2 to the
4.
perfect. You're using the rule in the other way. I know, you got to use the rule backwards. Great. When we pull the 2 out of this 2, what do we have left?
3.
Yep, just 3 to the 1. And then what about 5?
It's 5.
Good. What about for the 7?
2.
7 squared. Good. What about the 11?
2 as well.
And what about the 13?
4.
4 times 2 would be 8.
Oh, 2. I'm blanking.
That's okay. We're going to divide 6 by 2 for you, and we're going to get a 3.
3, right.
Right. I know it's late. I know. I hate to do it to you. But anyway, that's the game. And this is the work that you need to show to do that problem correctly.
Okay.
So you can go back and work on that again. All right. I hope that helps with standard factored form. You just got the whole
Yep.
lecture.
Yeah,
Great.
that's a lot.
Isaiah, do you have a particular question?
Yeah, I'm ready.
All right. We're ready for you.
My question is about proving statements with rationality and by the definition by mod. So my first question on special homework 6
Uh-huh.
says if x and y are rational,
Uh-huh.
then 2x plus 3y to the or 3y squared is rational.
Okay. Because some people were sick and are turning their homework in Monday, I'm going to make up a different problem. All right. But something similar. And we had a problem in the notes too. But that's okay. Let's do another one. All right. So proof if x and y are rational, then negative 5x squared plus 3y is rational. All right. So for direct proof, what would we assume?
X and Y are rational.
Yep, that's our hypothesis. We're going to assume that x and y are rational. And what do we wish to conclude?
Of that negative 5x is squared plus 3y is rational.
Right. So let's write our proof, shall we?
Mhm.
Assume X and Y are rational. And now we're going to write our wish. We wish to show negative 3x squared. Oops. Negative 5x squared plus 3y is an element of the rationals. There's our symbol for the rationals, okay? I'll just write it like that. Is that okay?
Yeah.
Mm.
All right, so it's Halloween. We hear the voice. Use the definition.
Definition.
So by the definition of rational, you tell me what we're going to write. We're going to get an equation for x and an equation for y.
Uh, X equals A over B.
I like A and B, where we got to say the whole thing because we're going to need
Where
all three parts.
A, B.
All
Can
right.
we say where AB is an integer or do we have
Yes.
to say, okay.
We
Or
have
you
to.
could write the words. Yes, you can write the words where A and B are integers, or you
Okay.
can use symbols. A and B are elements of Z, or you can read this. A and B are in Z.
Mhm.
What's the other
Where
thing?
B does not equal 0.
Exactly. And if you don't mind, I'm just going to use C over D for Y. And if I had a Z, I'd call it E over F. I would. Where C and D are in Z, and what else?
B does not equal 0.
That's right. All right, so I'm going to just take a little bit closer look at our wish because I always like to know exactly what I'm up against. What is it we'll have to show about negative 5x squared plus 3y before we'd be able to say that it's rational?
Mm,
Would it have to look like?
it could be R over S,
Uh-huh, R over S.
where R S is in Z and R S does not equal 0.
Yeah, so see, so now we know we're going to have to get this expression looking
Mhm.
like a quotient of integers with a
Right.
non-zero denominator. All right, so we're all set. We got all this great proof money, and we're just going to burn this, just like when I went to Target today and bought one dang little thing from the makeup thing and spent like, oh my God. Anyway,
Target is
Target, yeah. Is Target expensive?
yeah.
I just wanted to get one little like under eye concealer. It was like $32. I was like,
Yeah.
what? I'm like, oh man, this getting old stuff sucks even worse. It's expensive. Okay. So what do we do? What is the expression we need to now introduce into the conversation, folks?
Minus 5x squared plus 3y.
Yep, let's notice something about negative 5x squared plus 3y. And isn't it nice to see exactly what it is we need to look at? Because now we know, okay, we got to write that down and we got to do some stuff. All right, so Isaiah, you asked for this question. Help me. What should we write now on the other side of this equal sign?
Um, I don't remember. I don't know.
All right, I'm going to help you. I want to use this money.
Mm-hmm.
It tells me what X looks like. There's an X right there. Ooh, it's
Square.
squared. So
Yeah.
we're going to plug that in for that. And we're going
Uh,
to throw
or by
this.
substitution.
Yes,
Yeah.
yes. Now you're talking.
Yeah.
So the minus 5 just stays minus 5. We can't substitute in there, right? We wouldn't want to. But instead of X squared,
It would
we
be
can square
a.
A over B. Does that make sense?
Yeah.
Hmm.
Okay, great. Now plus, I'm just being real careful to write it down the way it is. And then the 3 doesn't need any substitution. But now the y is C over D. That makes sense? Now we got to deal with all this fraction stuff. Let's take a look. It can be nice to realize that any integer is just itself over 1. Do you agree?
Yeah.
Hmm.
And the rule about distributing an exponent goes for quotients of factors too. Oh, I think I called it laws before, so maybe I'll call it a law. Here's another law of exponents. If you have a over b raised to some exponent k, well, that's just a raised to the k divided by b raised to the k, okay? So that means that a over b squared is really a squared over b squared. And you can use the parentheses if you want, or you can drop them. It doesn't matter as long as we have the dot there. And then here we've got 3 over 1. Remember when we proved that every integer is rational? It's because any integer, like -5 or 3, can be written as itself over 1. And that's a quotient of integers. And 1's not 0, so the denominator's not 0.
Hmm.
Hmm.
Remember we proved that?
Yeah.
Yeah.
C over D. All right, so what do we have? We have -5a squared over b squared
Hmm.
plus, I haven't dealt with the common denominator yet. I'm trying to just sneak up on it. I'm trying to show you all the steps. Plus 3c over d. Because what we just did was we multiplied these two quotients together. And when we multiply fractions, we do it bikini style. Multiply the tops together, multiply the bottoms together. Okay? That's the rule for multiplying fractions. Same here. 3 times c on top, 1 times d on the bottom is just d. Are you with me?
Yeah.
Yeah.
And now we need a common denominator. So these are not numbers, they're letters. We don't know what they represent, so we're just going to assume worst case scenario, and we're going to assume B and D don't have any prime factors in common. So what is the common denominator? How do we even get it? Just multiply these two denominators together. When we multiply these together, how would we write that?
BD squared.
Oh,
Careful.
Oh.
B
Oh yeah, because
squared
D.
squared
Okay.
times D.
D. Great.
Yeah.
Now, right now, the -5a squared is over b squared. But we want to write it over b squared d, so we have to multiply it by the d, because that's what's missing in there. See what I mean? Does that make
Okay.
sense? I mean, what we just did right there was we took -5a squared b squared, and we basically multiplied it by 1. We multiplied it by d over d. See, this is just 1. It's perfectly legal to multiply something by 1. It doesn't change it. It just changes the way it looks. See, like if we were just going to look at this right now, we could cancel these D's and get that back. Does that make sense?
Yes.
Yeah.
All right, so what should we multiply the plus 3c times if we
B
want to
squared.
write it over b squared d?
B squared.
Yeah, the b squared is the missing part. Isaiah, do you follow that?
I have a question. I
Oh.
guess. I mean, yeah. I mean, I am following, I guess. Yeah. So it would be just the exact opposite, where it'd be 3C over D times basically one, but
Yeah, it's b squared over
B
b
squared.
squared is the one that we're using for this one.
So we're just okay. And
You pick,
then
you pick the one, the form of one that serves your purpose.
yeah, I got you.
Now that is now we got part one of the definition done because we've got -5x squared plus 3y written as something over something.
Hmm.
See what I mean? So this is part one of the definition of rational done. There's three parts to the definition, right? This is, part one where you write whatever it is as a quotient. Then we got to talk about the numerator and denominator. That's part two. And then we got to talk about the denominator not being 0. But we got the R and the S, even though R is complicated and S is a little bit too. But the point is, this is going to turn out to be an integer because
Hmm.
A and B and C and D are integers. and sums and products and differences of integers or integers.
Well,
See,
you
we
just
haven't used this yet. We're getting ready to use this and this. This is part two of the definition of rational. When we get ready to prove part two that this numerator is an integer and this denominator is an integer, in other words, when we prove the R and the S are integers, we use the part two of the definition of rational.
mhm.
We used the part one of the definition of rational. This is part one for X, this is part one for Y, to prove the part one for the expression negative 5x squared plus 3y. So use the part ones to get the part one. We're going to use the part twos to get the part two, that R and S are integers. And we'll use the part threes to get that this denominator, S equals B squared D, isn't zero. Shall we finish it?
Mm-hmm.
Yeah,
All right, let's write up the part two part. What do we need to talk about to open up the conversation about this whole numerator being an integer?
we need to talk about how well, yeah, you kind of just said it. We need to talk about how the first part of the definition we use A and B and C and D are elements of Z
Good,
to
let's write
prove.
that down. Since A, B, C, and D are elements of Z, good. And now what do we have to say? The, what are the operations being used here?
Uh, sums and product.
Yep, sums,
Product.
products.
And no,
And
and differences.
yeah, yeah, because we got a minus
We
sign
got a
here.
minus here.
Mm-hmm.
And even though it doesn't look like we're subtracting, you could put this over here and it would be subtracting. And differences of integers are integers. But I would let you get away with not saying differences because honestly, this is multiplying by minus 5 and that's an integer. So you don't actually have to say differences. But anyway, we did. It doesn't hurt to say it. We know. All right. And now we're going to tell our reader what we're calling these bits and pieces. We want to call this numerator R. R equals negative 5a squared d plus 3cb squared. I'm being real careful. And like, it's so easy to make a typo, right? So this is where we slow down, take a breath. And s equals b squared d are integers. I'm going to say r in, so I'm just going to say it like that, okay?
Mm-hmm.
Oh, that looks like int s. Ah, I don't like that. Looks like because of the s. I usually use imminent. I'll just say are integers. I don't want anybody to misunderstand. All right, great. That's part two of the definition of rational. Like, right, we're trying to prove that this expression is rational. We just established that the top and the bottom, the numerator and denominator, are integers. So that's part two. We're two-thirds of the way home to getting the definition of rational satisfied. The last part is we've got to talk about
Non-zero.
S not being zero. And S is built from B and D. So to address part three of the definition of rational, let's use part three of the definition of rational. See, we know B isn't zero. We know D isn't zero. If neither of these is zero, that product can't be zero. It's the contrapositive of the zero product property. Let's write it. But since B is not equal to zero and D is not equal to zero, S equal BD squared is not equal to zero by the ZPP, the zero product property. You should go back and look at the notes. And I think there was a website. I asked y'all to do a later. I said, do later, write the contrapositive of the zero product property. I think we even did it on the board uh, a few days later. And in WebAssign, one of the WebAssign problems was you had to write the zero product property in its contrapositive form. Do you remember that?
Yeah, I remember it.
Yep. And listen, if you need extensions on WebAssign, I can give you extensions all the way up to test 2 day, okay?
Yes, ma'am.
All right, so now we're good. So let's just wrap it up. What did we just prove?
That minus 5x squared plus 3y equals r of s.
Yeah, so that equals R over S, where R and S are
B.
integers. Almost wrote element of Q, and S not equal to 0, which means it is
Irrational.
rational by definition of rational. And there is how it's done, my friends. Thank you for going through that with me. Thank you for hanging in there. It's time consuming, but it's kind of satisfying. All right. So now the other thing that you wanted some help with, Isaiah, you were saying, there was another definition that you were having an issue with. What was that?
I believe it's divided by the definition of divisibility.
Divides. Oh, yes.
Yeah, by the definition of divisibility.
Yes. So proving statements involving the definition of divides.
I think these are actually the class that I missed.
That
I
makes
think,
sense.
yeah.
And I'd been promising a video, so now we have one. I was just having a hard time getting mo motivated because I feel like if I make an actual video that I need to log in with my phone too, and that
Mhm.
means I've got to look presentable. I never really feel like I look presentable on the weekend. That's my own problem. Okay. Hey, shall we review the definition of divides? Help me with that. Let's review the definition because we need that right in front of our very eyes. Uh, given, I'll set us up, integers, x and y, with x not equal to 0. So we're going to be dividing by x. Okay, it's going to be our divisor. I don't want it to be 0. We say x divides y. Think x divides into y. And do you know how it's denoted?
This was actually on the quiz, but
Yeah. So it's in the order that we read it.
yeah.
X, oh, I read. Oh, that's not good. That pen's not working out. Divides y. And it's really, really easy to confuse this expression with x with a slanted line y, which means x divided by y, which is a number. But this with a perfectly vertical line, it's got to be perfectly vertical,
Mhm.
is a statement that x divides y if y is equal to x times k for some integer k. So just some cautions. This notation, x divides y, is a statement, not a number. So it doesn't make sense to say that it's equal to something. It makes no sense to say something like x divided divides y equals r, where r is a number. That makes no sense because this isn't a number. It's a statement. So don't do this. Okay. So we must not confuse this notation, x divides y, with x divided by y, because x divided by y is a number. It's whatever the number is when you divide x by y. See what I mean? All right, so that's the first thing that gives students fits. It's just the notation. All right, so let's keep our definition up here where we can see it. And let's just uh work some real simple proofs. In fact, why don't we work through the solution to that quiz question? Okay. Prove this true statement concerning an integer n. If 6 divides n, then 3 divides n. Okay, we're going to prove it directly using this definition of divides. And it's already in if-then form. This is our hypothesis that 6 divides n. Here's our conclusion that 3 divides n. Well, maybe we should look at a couple of examples first. Let's just look at a couple of examples. I'll do it up here. 3 divides 12. Okay, 3 divides 12. Why? Because 12, which is the y, is equal to the x is 3. See what I mean? The x is 3. What is it? It's equal to 3 times
Three
some
times.
integer.
Oh, it's common here. Right.
Yeah, 4, right?
Or yeah.
And 4 is an integer. Let's do another one. Uh, if x is not equal to 0, then x divides x squared minus x, because this is our y, x squared minus x. X squared minus x is equal to x times what? X is an integer here. We factor x out of x squared, what's left behind? I'm factoring x out of this whole thing, but I'll start by just factoring x out of x squared. All right, so just think, what do we have to multiply this x by to get x squared back?
We said, what do I have to multiply x
Look,
by to get x squared back x?
yeah,
Oh,
I
yeah.
mean, yeah, I'm
Yeah.
trying to factor x out of x squared minus x. Can you do that? Uh,
Wouldn't you just
well, that's the
back
first
up?
step,
Yeah, just grab.
right? Because if we were going to distribute the x back across this parentheses that expression that we're building, we want to get x squared minus x back, okay? So we can kind of check it as we go. So when we factor x out of x squared, the remaining factor is x.
Mhm.
What's left over when we factor x out of negative x? All right, -1.
Okay, well,
Because now this, all right, and this is an integer because x is an integer.
da-da.
You know, x is an integer. An integer minus an integer is still an integer. Okay? Now listen, if you're having trouble like this, You're not alone, but you need to get yourself into Khan Academy online and start working through some of the basic algebra stuff. You need to get yourself into the tutoring center because if this is an issue, then you're not going to be happy, especially when we get into chapter 5. This is prerequisite knowledge, basic algebra, okay? All right, so anyway, that's a couple of examples. And here's an example of something that doesn't divide. 10 does not divide 5. This is the does not divide because when you 10 doesn't divide into 5 because 5, when you do try to divide it by 10, what you get is not an integer. You get 1/2. Okay? So here's, two examples of divides and one example of does not divide. You might want to get into the book and do a little reading. Did you read section 4.4? See, students don't want to read. This is section 4.4. It's worth reading. And I don't know if you remember, but I said if there's only one section in the entire book that you actually read, it should be 4.2. I hope you actually took the time to read that in the ebook. Do you know how to get into the
Yeah.
ebook?
I used the ebook on my Web of Science.
Well, you
Hmm.
need to use the ebook just to read. And if you're having trouble with divides, your first course of action is to read the book. She's a really good author. It's extremely easy to understand what she writes. All right. So if we want to prove this, we're going to use the definition of divides and we're going to assume our hypothesis. So what are we going to assume?
We're gonna assume the first. We're gonna assume the if.
There is no if in a hypothesis, although I know that you will be able to go online and find proofs where the first statement is a big if. It's bad form. Let's just assume this hypothesis. So let's just go ahead and suppose n is an integer, although that's a little bit more than we need to do because the minute we say assume 6 divides n, if we assume that that's true, then part of this being a meaningful true statement is that n is an integer. The definition of divides only applies to integers. So anyway, this is optional. But for sure, we have to say assume 6 divides n. What do we wish to show?
3 divides n.
All right, we're going to come back and we're going to revisit this wish because it's great that you know that that's what we wish. What's greater is to know what this actually means in terms of the definition of divides. Okay? So we're going to revisit that. All right, here we go. By the definition of divides, tell me what equation we can write based on our hypothesis, our assumption that 6 divides n. 6
Okay.
is playing the role of x, right?
Yeah.
And n is playing the role of y. So what can we write?
6. It would be we could do. You said so. The definition up there says y equals x for some integer k.
Yeah.
So
So, mm-hmm.
we would put our y.
So what is
Where
y when it's 6 divides n?
And
Just look at the position here.
it would be
and
n.
Okay, so what should we write for our equation?
You're right. N equals 6.
And you can use K.
Yeah, for some integer kids, yeah,
Great. Now
that
this is big progress. Being able to translate this statement into this equation is the critical step for working with the definition of divides. You with me?
Mm-hmm.
Because it's so critical and the definition of divides is quite tricky, let's now take another look at our wish and let's translate that wish into something more helpful. In other words, what does it mean to say 3 divides n? What do we really need to show before we would be able to say, yeah, 3 divides n?
what same n equals 3 times an integer. Do we J or I say we don't want to
Yeah,
use K
yeah,
then.
don't use K, but
Yeah.
Yeah.
even though technically it doesn't compile, I don't want to confuse myself because a little bit later when we sum things up, we might actually say that. All right, great. So this is our wish. This is what we have in our hand. But do you see how writing the wish, and in fact, sometimes I even put like a little dreamy wish cloud around my wish so I don't get confused between what I actually have in my hand and what I'm trying to get. But writing this tells us, oh, we got to say something smart about n. We're going to have to look at n. So let's do that now. We got to look at n and we got to show n looks like this. There'll be some work in between. Are you with me? You see what I'm saying?
Yeah.
All right, so you can say observe or notice. But the point is we got to look at n. Let's do that. So what do we know about n? We can't write this. That's what we wish. But what do we know about n? What do we have sitting in our math wallet?
N equals 6K.
Yeah,
Okay.
yeah, let's burn that. Let's use it. It equals 6K. Okay, we have something now that's closer to this than we were with just plain old n. Now see how seeing exactly what we need helps us get from where we're at n equals 6K. How can we get from this to n looking like 3 times some integer j? It's not going to just be a single letter, right? We know that by now. It's going to be some kind of expression. How do we get a 3 out of this? Well, do you see a 3 lurking hidden anywhere in this expression?
Yeah.
All right, tell me about that.
3. Um, and then J is gonna be
Well, don't worry about what j is.
okay.
Just you've extracted a 3, but what's left when you say I want to rewrite this so I can see a 3?
Uh,
What else do we have to write to make sure it's equal to 6K?
3 times 2.
Good. And then times the K, right?
Okay. Yeah.
Nice. So you have explicitly shown the 3. And now it's a little bit easier. We want the 3 to stand alone, and
Mm-hmm.
everything else is going to, go into our formula for J. What's our J going to be?
2 times K.
Nice. Oops, I need a period in there. Need a period out here. But this, see that, Isaiah? See what's going on there?
Yeah.
This is going to be our J. All right, so we've got part one of our wish. See, this is part one of our definition of, 3 dividing in. But now we've got to deal with part two. So we got to talk about this quantity that's our J quantity. So what should we say? Have we used all of our proof money yet?
Ah, um,
Ah.
you just
Ah.
you just say since
Yes.
since n wait well since the integer since integer so
Yes.
is since k is an integer or element of z.
And so what's going on to build J? What kind of operations? K is involved.
Oh yeah, products.
Yep. And
Products
products
of products are integers.
of integers are integers.
Yeah.
Now what do we write?
Oh wait, let me look back. I forgot
Look
like
at
my
your
format.
wish. See how, you went back and looked at what we have and,
Yeah.
look at your wish. What is it you need to say about? Say something about. See, we got that n equals 3 times something, and we got to talk about that something. See, this is
You
part of
see.
what is our, what is it? Why did we even do this factorization? So why are we even talking about K? Because K is in here.
Oh, we're proving that we're using the fact that k is an integer to prove that j is an integer.
Yes. So tell your reader what J is.
An integer.
Yeah, but what is J explicitly? J isn't just any old integer like a letter of the alphabet integer. J represents something very specific here.
2 times K.
Yes, J, which equals 2 times K. See, K is involved in the expression for J. That's why we had to, spin this, is an integer. J is an integer, but it's J equals 2K is an integer. All right, so let's see what we've done. Now we see that, well, what was it? Look at your wish. Your wish can tell you what you want to write. What did we just show? That n equals 3 times j, n equals, see, that's why writing this wish is so nice. You can actually just now read this as your kind of closing sentence. We just showed n equals 3 times j, right? Where j is an integer. Do you agree that we
Mm.
just proved our wish?
Hmm.
Which means what? Well, why were we even trying to do that? Look at the original wish.
Yeah, 3 divides
Yes, which means 3 divides n by definition of
divide.
yes. So you can help yourself so much by clearly writing your wish as a definition statement, because this is really what we're trying to do. We're trying to show 3 divides n, but to get to that place, we needed to show that n equals 3 times something that we could say was an integer. So these sorts of notations can really help point you in the right direction when you're feeling quite, lost. So I'm going to give you a do later, okay? And you can bring this back to Sunday office hour, or you can email me whatever you do, and I can take a look at it. Ah. So we just, use what you've learned here.
Okay. Ugh.
Thank you, Isaiah, for reminding me how tired I
Hmm.
am.
I still have one more question left on the Cengage.
Okay,
Something
well,
great value.
okay, so what's your question about Cengage?
Oh, let me double check to just see
All right,
this.
so you hold that thought while you're checking it, and I'm going to ask Maxine Joy since it's her turn.
Mhm.
Maxine Joy, what would you
Yes.
like to talk about next, if anything?
Um, I think I'm good for now. I just have to go over the notes for class that I missed on what day was it? Thursday. Um
You missed the lecture Thursday also?
yeah, because I think I emailed you, but I don't know if it came
Oh, that's
through.
right. Yeah,
I
that's
was
right. You
stuck
weren't
in the
there for the
traffic.
quiz.
Yeah.
Oh my gosh.
There was an accident on the 695 and it had backed up, so I was in there for like 30 to an
Oh, I heard
hour.
about that thing on the radio. Hey,
Yeah.
listen, let me ask you, Maxine Joy, you are in the 3:30 class, right? Or are you in the 2 o'clock?
I'm in the 2 o'clock.
Oh my gosh, I teach that lecture again at 3:30 right after your class, right?
Oh, I didn't. Oh, okay.
That's why I hang around because I teach it again. Oh my gosh, I wish you had known. You could have with the next class. So if that ever happens again,
Mm-hmm.
consider it to 3:30. Okay, just be sure and remind me that you're doing it because I won't remember. Since you're back to back, I won't remember. I might remember now that you've told me, that
Yeah.
you're at the 2 o'clock. But you can always come to the 3:30, and you can even take the quiz with the 3:30 if there is a quiz. If
Yes,
it's a
please.
test day, I would prefer not, but in a pinch,
Yeah,
I would
yeah.
let you.
There's for a test, no, but I try to get to campus early, but I don't know what's going on at 695. I feel like they've been constructing something since I was a freshman, and then
Oh,
I
it's going
don't.
to get worse.
But
Where are you
yeah,
coming from?
Gaithersburg.
Yeah.
Yeah.
Yep, yep, it's that way in PA too. It's construction, construction, construction. Jonathan, I'm not ignoring you. I saw you come into the office hour
Okay.
about quarter till. I know you're there.
I was just gonna let you know that I was about to leave the Zoom because I have to start getting ready to go
Ready
to
for
work.
work, and you're going to
Yeah.
work all night.
Yes.
God bless you.
Oh gosh.
I know.
Yeah.
That's
You
enjoyed
work you
so.
work night shifts? Like you work through the night?
Yeah, I work through the night, Monday to Friday.
And then she tries to come to school during the day.
Wow, bless you. That's a
Thank
hard line
you.
to toe.
It is.
All right, so Maxine Joy, are you going to be around Sunday?
Yes, I'll try to hop on Sunday.
All right, you
It's
can
gonna
email.
be at 8, right? Yes,
Yeah, yep. And now, email me and we
I
can.
will.
All right.
Thank you so much.
You're so welcome.
Have a good
You too. Isaiah, I'll take one more question.
All right, last question is my question is about the last part, the last question on the Cengage for 4.5 part one. Yeah.
Okay.
Um,
Hang on. Let me just catch up with you. I'm gonna just get in there and it's 4:4
yeah, 4.4 part two, 4.5 part
one.
one,
Okay.
yeah,
All right. Which question number is it?
16.
Oh, the last question. Ah, ah. Oh, yeah, that's kind of a nice one. Is it the one that says if A and B are integers and
Yeah,
12A equals 25B, is B divisible by 12? Is A divisible by 25?
yeah.
Mm-hmm. That's
Um,
This is the very same thing that I wanted to chit chat about.
no kidding.
um, I have well, my like for the first part of the question, I said the prime factorization for 25 is 5 to the second. And thus, by the unique factorization theorem, 12a contains the factor 5 2. And because, or let me say 5 squared, and because 5 squared is a factor of 12, it allows that 5 squared
5
is,
squared is a factor of 12?
now that I read
What?
it out, now that I read it out loud, I'm wrong. Like I'm wrong. Like, but I'm trying to figure out how do I guide through that question,
Well,
because it's kind of like
because reading, well, it sounds like reading out loud is a place to start,
not for sure.
right? Because then you can just, and do you sit with paper and pencil when you're working WebAssign, or do you try?
No, dude, Sengi.
Well, why not? Seriously, why not? How do you think what are you doing, air math in your head?
Yeah.
Oh, uh-huh. How's that working for you?
Oh, on this question, not so good, but I mean, the rest of them,
Don't even. Dude, what? Are you are you crazy?
that might be
No,
crazy.
you better not even. You better not even. Because if that's the case, thank goodness for special homework.
You know, special homeworks you get me right. And special homeworks kind of get me thinking. Those engages, if I don't like, I'll just like,
Engages.
I'll just zoom through it. What
I
was that?
like that. Sim gauges.
Engie.
Sim
That's what I call
gauges.
them.
All right, so what's your question?
If ambient energies and if ambient energy and total equals B.
All right, tell you what, John, what's your question?
Um, I guess basically I wanted to kind of
Jonathan, excuse me.
uh oh thanks.
I'm so sorry.
I
I'm so sorry.
That's all right. That's all right. I do go by Jonathan, but I don't mind if people
Oh, and I
occasionally call
didn't
me
mean to
John.
call you John.
Um,
Oh no, this question part B said upload a file.
Yeah.
that's right.
No, I didn't mean to. But anyway, go ahead.
Um,
I knew there
yeah,
was a
so
reason
basically I
why.
wanted to kind of just talk through it
Uh-huh. Okay.
and make sure that kind of like my thinking about it is right. When I was doing this before, I was a little tired and
All right.
coming
So
back to it now.
I'm
And
going to
so,
share my screen
yeah,
then. Let me share the screen and we'll look at it
sure,
together.
yeah.
All right. Let's take a look.
Because I know that I guess this is all hinging on the um, the unique factorization theorem. And um, like, right, I'm trying to zoom out from
Oh
the
no. Oh
articulation
no.
here.
I've got to view this as a student, otherwise all the answers. Oh no, it's too late.
Yeah, we both took screenshots,
Now you got well, if you
and
want
it's
to
already been distributed to the whole class. There's no going back.
oh yeah, you would be able to do that very efficiently. Oh well, if you want to cheat yourself out of the opportunity to learn it, what can I do?
Yeah.
What can I do?
If only I hadn't been a Boy Scout, and then I wouldn't have sworn to be a good guy.
Oh.
Um, so anyway, I guess my thinking about this problem, right? Okay, so um,
Oh wow, 5 factorial is one of the choices for the prime factorization of 25.
uh, um,
All right, so go ahead. Yeah, we're talking about
um,
prime factorization and unique
it,
factorization.
so if you've got some composite number, right,
Mhm.
then it's going to be expressible as a product of some power of primes per the this theorem that we looked at together the other day,
That's right, a
right?
product of powers of primes.
So I say to myself now, okay, both 12 and 25 are composite. Just taking those numbers by themselves. I say,
That's
okay,
right.
so
That's right.
I'm going to be able to split those up to 2 squared times 3 in the case of 12 and 5 squared in the case of 25. So far, so good. In trying to answer this question about the variables, at first I felt like, oh gosh, how do I approach this? But if we say the same thing about the product 12A and 25B as we said about 12 and 25 alone, then I think that's a way to make this comprehensible, right? So we have to say, okay, let's ask about B first. Is B divisible by 12? Um, a way that you could try to say that is, okay, um, 25B is going to be expressible as some set of prime numbers multiplied together.
right?
Or some
Yeah, let's write that down.
powers of
25B is expressible as a product of powers of primes, or we could even just say of primes, and then, you could gather them or not.
uh-huh.
Okay, so that's right.
I like your articulation here better, powers of primes. So then we can say, okay, what is that?
Yeah, what
What do
does
we
it look
know?
like? Right.
Right. So we know 5 squared is going to be in there, and then B is going to be something. We don't know what
Yeah.
that is yet, though.
So yeah, 25B is 5 squared times B. That's right.
So then looking at this question, is B divisible by 12? We
They
can
almost
say,
could have said is 25 divisible by 12 first.
uh-huh. Yeah, I think that's like the trick, it seems to me. Like I didn't or like I hadn't thought that through, and I went and read a section in the chapter, and they have an example that helped with this. So if if all of the prime factors of get consumed, so to speak, um, well, hold on. I think I articulated. Yeah, there we go. Good. Go ahead.
Yeah, I mean, 12 has to divide 25B because it divides, 12 is a factor of 25B and so is A,
Uh-huh.
right? So 12's got to divide into 25B. So 25B is 12 times some integer x.
Hmm.
But again, like you said, 25B is 5 squared times B. That has to equal 3 times 4 times x.
Hmm.
Well, the 3 and the 4 have nothing to do with 5. So the 3 and the 4 have to be factors of B because they aren't factors of 5
Yeah.
squared.
Okay, I see how.
But 3 does not divide 5 squared, and 4 does not divide 5 squared. So 3 has to divide B, and 4 has to divide B, and that means 12 divides B because there's nowhere else for the 3 and the 4 to fit. They can't fit into the 25.
Uh-huh.
And I'll,
And to
that's
frame it in like a hand wavy way, like it fits. It doesn't fit here and it doesn't fit there, or like
right.
this part of it and that part of it don't fit over here. So it's got
Yeah.
to fit in the other slot. What is the other
Yeah.
slot?
Yeah.
B.
Yeah. The other, yeah. And so we're using the word fits, which is, highly technical, but we
Uh-huh.
could say is a factor of, the 3 has to be a factor of 5 times 5 times B. Well, the 3 sure is not a factor of the 5 times the 5, so the 3 must be a factor of B.
Mm,
And or 3 doesn't divide 5 squared, so it has to divide the B.
That's nice.
But 3 does divide 5 squared B. And 4 does divide 5 squared B. So this is what has to happen. Since 3 and 4 both divide B and they don't have anything to do with each other. It's not like, 2 divides B and 4 divides B. Well, the 2 could be fit, could be in the 4. It doesn't mean there's, but the 3 and the 4 being relatively prime force their product to divide B. And that's not very nice the way it's written because somebody's going to look at that and say, what the hell does that mean?
Mm.
With a window or something, they'll think, what? They're drawing a.
I get it.
Do you? All right,
Yeah,
so
yeah.
I'm gonna leave you with a little word of advice. Where I don't know how you sit and work on your web assign. I know if you're sitting, with your laptop in your lap, then you don't really have a place for pencil and paper. So I recommend a table, a flat surface, that's large enough for you to have pencil and paper on the side so that you can really crank out some of the work. That's just my recommendation. What do I know?
And then for B, just like upgrade, like upload a picture of my work for it.
Yeah.
All right, I'm good. I'm good.
Good. And then I'll be, I knew there was a reason why I didn't usually assign this problem, but I got all excited and didn't scroll all the way down to realize it was a file submission problem. But that's okay. I'll open them up and I'll score them and I'll load. That'll give me something else to do this weekend or
But
well, yeah, I got the quizzes graded. Wow. What a shock and surprise. I had no idea. I don't know. I mean, we had that quiz on Tuesday and Monday, at least the first two questions, right? They were exactly the same as our do now, right? When I said, hey, we're not having a quiz, but if we were having a quiz, this would be the
uh-huh.
quiz. And all I did was change the third problem. So I thought everybody would at least get the first two. Anyway,
So I have a question, right? You dropped the lowest two quiz grade, right? The lowest two quiz
have
grade.
you read the syllabus?
Yeah, I read the syllabus. I was just making sure.
Are you secure in your ability to read the syllabus?
Yes, man.
Well, I'm glad to hear that.
I'm just let me
No,
kind
no, yeah. Listen,
of.
I mean, life happens.
Yeah.
Dropping the lowest two quizzes really is for a variety of reasons. Maybe you fell behind a couple of days, so you don't do well on a quiz. That's fine. Or maybe, traffic keeps you from getting to class. Uh, but for folks that consistently miss the beginning of class, the first 10 or 15 minutes, uh, the quiz tr- is supposed to help encourage timely attendance
Hmm.
because those first 10 or 15 minutes are, I think, fairly important because that's when we kind of just start thinking about what is the topic of the day and why do we care?
Hmm.
I shoot for that. I don't know if I achieve that, but I shoot for that.
I got you.
So anyway, but your attendance is good. I see you back there all the time.
Now I gotta start coming to the front.
Hey, I noticed it looks like you might need some glasses, man.
Yeah, nah, I went to, I know it's crazy. I went to the doctor's office today to get some glasses. I ordered my prescription.
Oh, I'm so glad.
Nice.
I'm
Yeah,
so glad because I've
yeah,
been worried about you, back there. But there's plenty of space up front. There's like two or three seats right up front. I would love to have you move up closer to the front.
yeah. There's more extra credit in the front.
The front is where it's at.
The front is where that's where all the studios. I mean, not, but that's where all that's a good environment to be in.
Mhm.
I agree. I think it is a good idea to sit, closer to the front than the back of a math class.
Yeah.
You know, uh, it's hard to reach and get eye contact with everybody in a big class, but certainly it is more challenging to get eye contact with somebody that's 20 feet away, 15, 20 feet away. It's hard. It's harder. All right, it is 9:36. Jonathan, I really appreciate your coming, and I am so sorry that I do not have the energy this evening to go any further. I'm going to go ahead and say this
Oh, no worries.